Afternoon, friends. Yesterday we have seen the introduction of the pressure vessel. Also, we have seen the unfired pressure vessel and fired pressure vessel. Types of welded joint used in pressure vessel. We have seen the class 1, class 2 and class 3 categories of classification of the unfired pressure vessel as per the class. Then we have seen the different categories of the welded joints in unfired pressure vessel: category A, category B, C and D. Then also we have seen the selection of the material for unfired pressure vessel. And finally we have seen selection of the design parameters for the unfired pressure vessel. The today's lecture will going on the component of the pressure vessels. Okay, which component included in the pressure vessel? Cell, unfired pressure vessel cell. Unfired pressure vessel cell. Then there are different types of the end closures are used. Then next is we are using the number of nozzles and openings. Then flange joint, and last is a vessel support. Different types of the vessel support as per the vessel. If there is a vertical vessel and horizontal vessel, as per that types of the vessel will select the vessel support. Okay, this is the main component of the unfired pressure vessel. And next, see the pressure vessel cell subjected to the internal pressure. Okay, the thickness of the cylinder of the pressure vessel subjected to the internal pressure Pi is determined on the basis of the thin cylinder. Already we have seen that in the design of the cylinder. Okay, the analysis of the unfired pressure vessel, the mean diameter of the cell is taken instead of the inner diameter of the cell. Remember that. Okay, the design of pressure vessel cell is discussed under there are two conditions, different conditions. Okay, pressure vessel cell subjected to the internal pressure Pi, and second condition, pressure vessel cell under combined loading because of weight of the cell and contents of the cell. Okay, pressure vessel are subjected to the internal pressure Pi. Okay, sigma T is the tangential stresses. It is also called as a circumferential stresses or hoop stresses. Already we have seen. If I have taken cross section of the pressure vessel, then there are different types of the stresses are induced inside the cylinder. Okay, sigma all is the allowable tensile stress for a cylindrical vessel is given in Newton per mm square. Pi we are consider here internal pressure. It is also called as a design pressure. Okay, this is given in Newton per mm square. Di is the inner diameter of the cylindrical pressure well. This is given in mm, and L is the length of the pressure vessel, and D is the mean diameter. This is the second part, pressure vessel cell under the combined loading. We use the D is the mean diameter of the cylindrical vessel cell. This is also given in mm. How to calculate this mean diameter? We will calculate with the help of Di plus T, internal diameter plus thickness of the cylinder. With the help of this formula we can calculate the mean diameter of the cylindrical vessel. Okay, See, pressure vessel cell subjected to the internal pressure, again cylindrical pressure vessel cell, as the we have seen the same thing is here. Okay, sigma T and sigma R already we have find in the design of pressure vessel. Sigma T is equal to, we know that, Pi into D divided by 2T. Okay, we know this formula, sigma all or sigma T is equal to, where mean diameter D is equal to, already I have told, Di plus T. Considering joint efficiency, here you should consider the joint efficiency. This efficiency is denoted by the NL. Okay, longitudinal joint efficiency. N is equal to sigma T is equal to, you will get the Pi into bracket D is equal to Di plus T, put in that equation, divided by 2. Then you will get the shell thickness of the pressure vessel. Okay, how to calculate that shell thickness? Adding the corrosion allowance, the thickness of the cylinder vessel, then you will get Pi Di divided by 2 sigma all NL minus Pi plus C. C is the corrosion allowance. Remember that C is the corrosion allowance. We want to consider that corrosion allowance when you design the pressure vessel. Okay, then spherical pressure vessel. Second is a spherical pressure vessel. The thickness of the spherical pressure vessel shell is TS. It is denoted by the TS. Okay, TS is equal to, you will get Pi Di divided by 4 sigma all into NC. Okay, by mistake I have write here NT is there. This is the efficiency of the joint minus Pi plus C. Again C I will explain what is mean by TS. TS is thickness of the cell with corrosion allowance C. Okay, sigma all allowable tensile stress for the spherical vessel cell. This is given in Newton per mm square. Pi is the design pressure or internal pressure, Newton per mm square. Di is the inner diameter of the spherical vessel cell. Okay, Di. This is given in mm. Okay, don't confuse. And NC is the efficiency of the joint, and C is the corrosion allowance. Okay. There are different load acting on the cylindrical pressure vessel cell. Okay, due to internal pressure of the fluid. Second is weight of the vessel with its content. Okay, whatever may be weight of the vessel with its contents. Okay, that's why you will get the different load acting on the cylinder. Then third is a wind load. Okay, and fourth is a load due to the offset piping. Okay, load due to the offset piping. That you should remember the fourth thing, different loads acting on the cylindrical pressure vessel cell. There are 4 loads. Okay, this once TS is estimated, what is mean by TS? Thickness of the cell. Okay, is necessary to determine the resultant stresses induced in the cylinder due to the combined loading. Okay, which type of the stresses are induced in the cylindrical vessel due to the combined loading? Okay, stress in the circumferential, or we can say the tangential stresses. It is denoted by the sigma T. Stresses due to the combined loading, first is a sigma T. It is called as a tangential stress. And stresses in the longitudinal direction. Already there are two things we have seen in the cylindric design of the cylinder. Okay, stresses in the longitudinal direction due to the internal pressure. Okay, these stresses are developed in the cylinder due to the internal pressure Pi. Okay, stresses in the longitudinal, again due to the weight of the vessel and its contents in vertical pressure vessel. Remember that there are two types of the pressure vessel. Okay, where we'll get the sigma L in the horizontal pressure vessel, vertical pressure vessel, due to the weight of the vessel and its contents, okay. Again, combined stresses or bending stresses due to the total weight of the vessel and its content in the horizontal pressure vessel also same thing. Bending stresses is induced due to the total weight of the vessel and its contents in the horizontal pressure vessel, or due to the, there are again two types of the loads in the horizontal pressure vessel, vertical pressure vessel: seismic load and wind load. Okay, again third is there is a torsional shear stress due to the offset pipe fitting. Okay, when you doing offset pipe fitting, then there is a torsional shear stress are induced. It is denoted by the tau, remember that. And last is a resultant stress. Okay, it is denoted by the sigma r. Resultant stress, it is denoted by the sigma r. Then stresses, how to find out the stresses induced in the circumferential, then longitudinal, then torsional shear stress and resultant stress. We will see the one by one. Stresses in the circumferential direction, it sigma t is equal to, already we have seen, pi into d. D is the mean diameter, it is equal to di plus t, internal diameter of the cell plus thickness of the cell, divided by 2t, in which tensile. Okay, t is the thickness of the cylinder vessel shell. We are not consider here corrosion allowance. Remember that if the corrosion allowance are considered, then there is a c is there. Okay, thickness, then t is equal to what you will get, t is equal to ts minus c is there, ts minus c. Okay, cell thickness minus corrosion allowance, this t here you will get. Remember that, this is important. Thickness of the cylindrical vessel shell with the corrosion allowance is denoted by the ts, and corrosion allowance is denoted by the c. Okay, this is the first stress. Okay, stress in the circumferential direction. Second is a stress in the longitudinal direction. Okay, sigma L is the longitudinal direction. Why this stress is developed? Stresses in longitudinal direction is developed due to the internal pressure Pi, and it is denoted by the sigma L. Okay, there are two types of the stresses induced in the longitudinal direction, due to the internal pressure and due to the weight and its contents. That's why we'll write here sigma L1 is equal to, due to the internal pressure, the longitudinal stresses are induced in the given pressure vessel. Sigma L1 is equal to pi di divided by t. Pi di divided by t. Okay, all of you getting? Pi di divided by 4t. Okay, in the tensile. Okay, second is a due to the weight of the vessel and its content in the vertical pressure vessel. Second stress is induced in the due to the weight of the vessel and its contents in vertical pressure vessel is denoted by sigma L2 is equal to plus or minus W divided by pi into bracket di plus t into again t. Okay, there are two sections. I will explain in details. There is a section A and section BB. There are two types of the stresses are induced, below the support and above the support. Okay, because of weight of the cell and attachment of that vessel. Okay, there is a tensile or compressive stresses are induced. W is given for weight of the vessel and its content. This value is given in Newton. Remember that. This is very important, these two formulae, stresses in longitudinal direction. We have seen in the figure of the vertical pressure vessel, stresses in longitudinal direction due to the weight in vertical pressure vessel. Okay, the weight of the pressure vessel and its contents is induced in the compressive stresses in the part of vessel cell. The support, you have given the support and section AA, and the tensile stresses in the part of the cell below the support BB. Okay, shown in the figure. W is the weight of the vessel shell and attachment above the section AA. Okay, and second is the at the section BB of vertical vessel shell below the support. W is the weight of the vessel shell and attachment of the section below the section BB plus weight of the fluid. Okay, remember that both things, the above the section AA and below the section AA, which you will get weight of the vessel cell and attachment, and where we will get the addition of the total weight of the fluid. And third is a bending stresses due to the total weight of the vessel and its contents in the horizontal pressure vessel, or due to the wind load and or seismic load vertical pressure vessel. Okay, both horizontal and vertical pressure vessel. Already we have calculated sigma L1, sigma L2. We are consider here sigma L3 for the maximum bending stresses induced in the given pressure vessel. Okay, how to calculate that bending stresses? In the SOM subject also we have seen the relation bending stress or maximum bending stress is denoted by MB. The MB is the maximum bending moment. Okay, and Z is the sectional modulus. Okay, sectional modulus is about the axis perpendicular to the longitudinal axis of the vessel. Okay, this value is given in mm cube and M is given Newton per mm. Movement means what? Force into distance. Already we have seen in the SOM subject. Okay, then how to calculate the Z value and EM value? Okay, Z value will calculate Z value with the help of you know that the sectional modulus about an axis perpendicular to the longitudinal axis of the vessel. Okay, there we are consider the cylinder having the external diameter DO and internal diameter DI. Okay, we require the external diameter. It is the ratio of moment of inertia about the x-axis and to the distance from the centroid. Maximum distance from the centroid means it is denoted by the y max. What is the moment of inertia about the x-axis? If you have considered the cylinder, then you will get that value pi r cube divided by t. In circular section is there. Okay, pi r cube into t. And what is the maximum distance? Means half distance from the centroid to the base of the vessel. You will get the do by 2, total diameter divided by 2. If you are solving this equation, then you will get the z is equal to pi divided pi into d by 2. R is equal to, we can write d by 2 cube into t divided by do by 2. Again, if you solving this equation, then you will get the pi d square t divided by 4. Then again you can put the value of mean diameter of the cylinder, d is equal to di plus t. Already we have seen z is equal to pi into di plus t, pi into bracket di plus t square into t divided by 4, okay. This is the value of z. Then put the value in that equation, mb divided by z. Then you will get the sigma L3 is equal to plus or minus 4 mb divided by pi into bracket di plus t square into t, tensile or compressive. That's why I have written here plus or minus, okay. R is the mean radius of the cell. That's why I have written here R is equal to d by 2. This value is given in mm. Then total stress in the longitudinal direction, we have calculate sigma L1, sigma L2 and sigma L3. Then you will get the total stress in the longitudinal direction, the summation of sigma L1 plus sigma L2 plus sigma L3. This may be tensile or compressive. Then last is a bending moments acting on the horizontal pressure vessel cell because of or due to the weight of the vessel and its contents. Then how to calculate the bending moment acting on the horizontal pressure vessel? Okay, see in the figure, due to the total weight of the vessel and contents, we will get the maximum bending moment. All of you getting? Remember the formulas. See the figure. Okay, in the bending load of the horizontal pressure vessel due to the total weight and total weight of the vessel and its contents or liquid. Okay, the formula is m is equal to wt divided by 16 into bracket d square plus 2l square minus 4h square. Okay, here is a capital H. By mistake I have written small h. Remember that this capital and small h is same, divided by L plus 4h divided by 3 minus 8a. Okay, what is Wt? This is the total weight of the vessel and it contents. Okay, this weight is given in Newton. Remember that. D is the mean diameter of the cylinder vessel shell. Okay, this value is given in mm. L is the length of the cylindrical vessel shell. This is also length is given in mm. H is the depth of head. This is given in mm. And A is the distance from the depth of head to the support. Okay, all of you getting? There is no derivation. You have to remember this formula. On the basis of that formula, you will get the numerical. Okay, same figure is here. Remember that. Bending load on the horizontal pressure vessel cell due to the total weight of the vessel and its contents. Okay, bending moment acting on the vertical pressure vessel also. Bending moment acting on the vertical pressure vessel. Okay, the formula is mw is equal to fw1 into h1 minus x h1 minus x divided by 2 plus fw2 h1 minus x plus h2 divided by 2. Okay, from the given figure, the bending moment mw acting on the vertical pressure vessel cell. Okay, fw is acting on the vertical pressure vessel cell at a distance x. See here, the distance is shown x. Okay, from the bottom due to the wind load. Okay, wind load. Then you will get that equation. fw1 is the force due to the wind load acting on the lower part of the vessel. This is given in Newton, and you will get the formula fw1 is equal to, you can write p1 into bracket h1 minus x into do. Again, what is the p1? P1 is the wind pressure, the lower part of the vessel shell up to the 20-meter height. This is given in Newton per mm square. Here I have explained what is meant by P1 and P2. Before going on that, we will see the FW2. Force due to the wind load acting on the upper part of the vessel. I have divided this vessel into the two parts, H1 and H2. Again P1 and P2. Okay, you will get the FW1 and FW2. FW2 is equal to P2H2 into DO. P1 is the wind pressure for the lower part of the vessel cell up to the 20-meter height. Already I have told. Okay, to the 20-meter height. This value is 4.623 into 10 raised to minus 8 v square w. V suffix w square. Vw means what? Wind speed. This wind speed is given in meter per hour or kilometer per hour. Remember that. This value is given. V suffix w means wind speed is given. Okay, and P2 is the wind pressure for the upper part of the vessel shell above the 20-meter height. Okay, remember that. This value again 4.623 into 10 raised to minus 8 Vw square. Okay, Vw is the wind speed. This is given meter per hour or kilometer per hour. In that figure also dO is the outer diameter of the vessel. This is given in mm. First figure I have shown for the wind load, and second figure I have shown for the seismic load, bending load on the vertical pressure vessel. We are consider when you design the vertical pressure vessel, then you should remember you have to consider wind load and seismic load. That without that two load you can't design the pressure vessel. Okay, then next again bending load on the vertical pressure vessel. Here I have shown H1, H2, FW2, F1, P1, P2, and DO is the diameter. See how to the forces is act in the wind load and seismic load on the vertical pressure vessel. Then again third is a torsional. Okay, torsional stress, shear stress induce the longitudinal direction. Okay, total stress in longitudinal direction. Okay, tau is equal to torsional shear stress. Why will get the torsional shear stress? Due to the offset piping. It is denoted by the tau. Tau is equal to T divided by J into R max. What is T? T is the torque about the longitudinal axis, or we can say the axial axis of the vessel due to the offset piping. This value is given Newton meter or Newton mm. Torque is given. J is the polar moment of inertia, okay, of the vessel cross section about the longitudinal axis. This value is given in the mm raised to 4. It is the summation of Ixx plus Iyy. Already we have seen in the SOM subject, okay, how to calculate the polar moment of inertia. Then we'll get J divided by R max. J divided by R max is equal to polar moment of inertia 2 pi r cube t divided by dO by 2. Already we have seen this equation is equal to 2 pi. R is equal to again mean diameter of the vessel. That's why I put R is equal to d by 2. D by 2 bracket cube into t divided by dO by 2 is equal to, if you are solving this equation, you will get pi d square t divided by 2. Again, if you are solving this equation, J by R max is equal to pi into bracket di plus t bracket square t divided by 2. Then put this value in that equation, tau is equal to T by J by R max. Then you will get the shear stress, tau is equal to 2T divided by pi into di plus 2 square bracket square into T. This is the third stress we have seen induced in the given pressure vessel due to the offset piping. Okay, it is denoted by tau. Then next is a last stress is a resultant stress. Okay, pressure vessel cell is subjected to the direct stresses we have seen sigma t, sigma l and torsional shear stress tau. According to the distortion energy theory, already we have seen that theory. Resultant stresses induced in the cylindrical pressure vessels are sigma r is equal to root of, there is a whole root for that equation, in bracket sigma t square minus sigma t into sigma l plus sigma l square plus 3 tau square. Okay, remember that equation. We are use that equation for the resultant stress induced in the pressure vessel cell. Okay, then for the safety of the pressure vessel, following condition we are using, this condition must be satisfied. Okay, sigma r, first condition, sigma r is less than or equal to sigma all. Okay, sigma all is the allowable tensile stress. This is given in Newton per mm square. This condition should be satisfied. Then you can design the pressure vessel. Okay, remember that. See, check that your answer. Sigma r is less than or equal to sigma all. Then second condition, sigma t is less than or equal to sigma all. Again tangential stress is less than or equal to allowable tensile stress. Fourth condition, sigma t, sigma l, this is given in tensile. There are two conditions for the tensile and compressive. Sigma l tensile is less than or equal to sigma all, and last is a sigma all for compressive is less than or equal to sigma all c. C means what? Compressive. Okay, remember that allowable compressive stress is given in Newton per mm square. Okay, this is for the compressive stress. All of you getting? This formula is very important. Okay, you should remember all the formulas. With the help of that formula, you will get the one question for the 18 marks in the end sem examination. Okay, remember that you will get the one numerical for the 18 marks or 16 marks. This is very important. Today we'll stop. Next lecture we'll see the types of the head. Design of there are end closures is given in the pressure vessel. Okay, types of the end closures. There are two types of the end closures, flat head and form head. Today we'll stop here. Next lecture we will see the details. Thank you.